Recording is rolling. It is Wednesday, November 13th. We're going to do textbook puzzles today. You guys got chapter 10 from your book is Energy, Work, and Simple Machines. Chapter 11 is Conservation of Energy. And so have those out. But just like normal, we're only going to do the ones that I circled. We should be able to do most of those in class today, I think. And then I'll pick those up from you guys on Friday. So there might be like one, maybe two at the end that we don't fit in class. And if that's the case, then I'll set you guys up how to solve it. And then you guys can turn this in by the end of the week. Tomorrow it's going to be a mechanical advantage lab. So let me show you guys that. I got a couple of posters here. So you guys have at least a day to think about this. Okay. So here's what I'm calling a 3-to-1 mechanical advantage system with pulleys. Right? And I got a pulley system in front of me too. You guys see this is in operation? Okay. So you guys see it only takes a small input force to lift a very heavy weight right here. Okay, let's talk about it. Now I'm going to go back to my poster version. This is cartoon version. Okay, suppose this right here weighed 300 newtons. You guys see that? 300 newtons. What would be the tension in the string? Huh? Okay, so this weighs 300, but it's being split three ways. So the tension is only 100 newtons. Okay. Now, as long as there's no frictional losses, nothing like that, how much force do you have to pull on the side of the spring scale to lift it? 100 newtons, right? Because that matches the string tension. There's only one tension, that one string. Yeah. Okay, so do you guys see you only need 100 newtons of force to lift something that's 300 newtons? Did your strength just magnify by a factor of 3? That's a 3-to-1 mechanical advantage. Okay? Now, you don't get something for nothing. You cannot amplify the amount of energy in the universe, right? So do you guys see this principle up here? It says work in equals work out. You guys know work is force times distance. So let's look at, guys, how do you pay for that increase in strength? You pay for it in terms of what? Distance. Boom. Here, I'll show you guys my live version. If you're in class, you can see this too. You guys see as I pull the spring scale, I'm pulling it a long distance, but that really heavy weight is only moving a little bit at a time. You see that? All right. All right, so same thing here. Let's throw in another set of numbers. Okay, suppose I want to lift this really heavy weight, 10 centimeters. How many centimeters does string do I have to pull on the side of the scale? 30 centimeters, right? It's still a 3-to-1 ratio, just the opposite way. You guys that too? Okay. Now, mechanical advantage. There's two different perspectives on mechanical advantage. There's what's called ideal mechanical advantage. If you just look at the distances, so this goes up 10 centimeters, have to pull 30 centimeters. That's based on the geometry. You can look at the picture and get that from the geometry, right? Now, there's another perspective called actual mechanical advantage, which is the ratio of the forces. Now, in my numerical example, I said it should also be a 3-to-1 ratio, right? 300 newtons, 100 newtons. Maybe I was lying to you guys just a little bit because there might be a little bit of frictional loss, or maybe if these strings aren't exactly vertical, there's a little bit of trigonometry. So maybe the input force is maybe a little bit more than 100 newtons. Maybe it's like 110 newtons, something like that. Right. One more value you can do. If you take the ratio of these mechanical advantages or the ratio of the work out compared to N, you can get something called efficiency. Like how efficient is this? Now, if it is 3-to-1 both ways, if this is 3-to-1, this is also 3-to-1, that would be 100% efficient. But realistically, tomorrow, I bet you're going to get maybe like 90, 95% efficient, maybe something like that. I'm going to scan these. I'm going to run these to the scanner later today. And then tomorrow, I'll give you guys one of these, okay? You'll have one of these tomorrow. You're going to rig up each one of these. Now, guys, each one of these is a different mechanical advantage. We just look at this one. This one's 3-to-1. You guys see a 3-to-1? Okay. Here, a quick rule of thumb is look at the movable pulley compared to the fixed pulleys. You can see it in class. Guys, look at my one in class. You guys see 3 red pulleys? You guys see these 2 ones are fixed in place? But not this one. This one's moving up and down. Is this a movable pulley? Right? Let's look here. So this movable pulley has 1, 2, 3 strings up. So the weight's split 3 ways. So that's a 3-to-1 advantage there. Right? How about these other ones? Guys, what is this advantage here? Mechanical advantage. Huh? 2-to-1, 2-to-1. Now, there's more than one way to do a 2-to-1. You don't have to do exactly this, but you could, right? You guys see 2 strings up for 1 down. So as I pull this, I bet the distances are a ratio of 2-to-1. I bet my strength, but the forces are a ratio of 2-to-1, just the other way. Okay. What's this advantage here? 1-to-1. There's no advantage at all, other than you get to change the direction of the force, right? But if this weighs 100 newtons, you still have to pull with 100 newtons to lift it. So you haven't really increased your strength at all. Right? So 1 to 1, 2 to 1, 3 to 1. What's this guy right here? Could that be a 4 to 1? You guys see 1, 2, 3, 4 strings going up from this movable pulley? Right? Also, I have some double pulleys not within reach I can put in front of the camera right now, but there are some double pulleys. Right? So these two could be effectively just one, and the two wheels move independently of each other. All right, so you guys get to think about that tonight, and that'll be tomorrow's lab. We'll be doing that. Are you guys good with that so far? All right. Then on Friday, Justin's in the auditorium. So this is for juniors and seniors. Since almost all my students are juniors and seniors, I kind of have to plan around this. I think in class I'll probably be doing a Kahoot in class. So anybody who's out can just watch the video and probably be all right, right? But here's how they're divvying this up. So going to the auditorium, period 1 is juniors, last names A through L. Period 2, juniors, last names M through Z. Period 3, seniors, last names A through L. Period 4, seniors, last names M through Z. I don't know what they're going to be talking about. Students have been asking me today. I know Justin does a lot of stuff, though. I think they do stuff with graduation gowns and yearbooks and photographs. I think they do all those things, right? I'm going to guess they're going to mention graduation gowns somewhere in there to help you guys get ready for graduation, but I don't know for sure everything they're going to talk about. That's Friday. All right. I will get you guys your next take-home quiz by the end of this week. Not today, but by the end of this week. And then I did tell you guys a few weeks ago, I want to give you guys 2 in-class quizzes before the midterm. And the first of those is going to be next week. So not on Monday, but sometime after that. It's going to be mostly on forces. There's a couple of projectile questions. There's a couple of energy questions, but it's mostly centered on forces and Newton's laws of motion. And how about this note? Allowed 1 paper of notes. So if you guys have, say, like just a piece of paper, it could be a blank paper, it could be a notebook paper, whatever you want, right? Any formulas you guys want to write, any examples you guys want to write, you guys can bring into that. Right? So it'll be multiple choice. I think the questions are a little bit easier than I tend to ask you guys, but yeah, it'll be that. Right. So you guys good with what's coming up next few days? All right. So let's dive into these puzzles right here. Start on chapter 10, energy, work, and simple machines. All right. So we're just doing the ones that I circled, just like always. Right. Number 52, the 3rd floor of a house is 8 meters above street level. How much work is needed to move a 150 kilogram refrigerator to the 3rd floor? 52. Okay, maybe I want to draw this out, think about it. So I got this fridge. Has a mass of 150 kilograms. Ooh, guys, how much does this refrigerator weigh? About? Yeah, 1,500 newtons. Yeah, because 150 kilograms mass, about 10 meters per second squared gravity field. I usually round it to that. Let's call it 1,500 newtons weight. Right now, if I stop right there, what is this fridge doing? It's a free fall. Right, so that's not good. I want to lift this up. Guys, how much lifting force do you need to pick up this refrigerator? Suppose you're picking up at constant speed. That 1,500 newtons right there, right? Okay, so I need to lift with 1,500 newtons. Okay. Then I'm going to lift it to some height. I'll call this the height. How much do they say? 8 meters. Height equals 8 meters. Okay. And the question is how much work? Right. Guys, what's the formula for work? Work equals what times what? Force times distance. That's right. Force times distance. You're going to see this formula a bunch today. No, specifically a dot product. You guys remember what dot product means? It means you only care about the components that are in the same direction. Right? But that's true in this case because you're lifting straight up and the refrigerator is also moving straight up. So the angle between those is 0 degrees. Guys, what's cosine of 0 degrees? 1. That's an 100%. Here, I'll show you guys that on the calculator. If I do cosine of the 0 degree angle between those two vectors, it's equal to 1 as in 100%. So you don't even have to really consider the business stuff. Right? But I do want to show you guys, before I start plugging in numbers, is an alternate way to think about this. Guys, is this force always equal to this weight as long as you're lifting at constant speed? It is. So in place of F, I'm going to go mg. And guys, the distance we lift it, oh, isn't that the height we end up giving it by the end? So in place of d, I'll call it h. And oh, look at that. Guys, what is that an expression for? Potential energy, right? MGH. Do you guys see? This is a point I made before. This is just a little bit of review. Whatever work you do lifting the refrigerator is equal to the potential energy you end up giving it by the end. That's where all the energy went. Okay. So let's put in 1,500 newtons of lifting force, and we're raising it 8 meters. So my calculator screen is telling me this number right here. But guys, that number has units attached. What should I write? 12,000 what? Joules. Oh yeah, because joules measures energy. Right? It's newtons times meters. That's joules. Right? Ooh, could I express this with a prefix? Guys, that's 12 what? Huh? Kilojoules? Right, 12 kilojoules? Either of those is okay. They're the same thing. All right, you guys get on 52. Lift in the fridge. Number 66, lead. Diego pulls a 4.5 kilogram sled across a level snow. So level is important because there are no hills, so you don't have to think about gravitational potential energy. Level snow with a force of 225 newtons on a rope that's, ooh, look at this here, 35 degrees above the horizontal. There's an angle here. If the sled moves a distance of 65.3 meters, probably straightforward, right? How much work did Diego do pulling the sled? Okay. This reminds me of a poster. Let me dig through these posters here. Here it is. Here it is. Right. Actually, I think this one's going to be good for a couple of these days. You guys see this pushing this shopping cart right here? Right. So if I push on some weird angle and the cart only moves directly forward, if I do F dot D, force dot distance, I have to consider this angle between them. Here's one way to think of it, is that my pushing force, not all of it moved the cart forward, only the forward cosine component did. Is that true? You do F cosine theta and then times the distance the cart goes. That's all the work that was transferred into the cart. Right? I need that cosine. Right? Now, here with the sled, instead of pushing down and forward, we're pulling up and forward. But it's the same idea. The theta could be up here. This would be the angle theta right up here. It's the same idea. Right? Let's just do that. So this is 66 sled. At the sled, got this force, which is 225 newtons. Okay. This is 35 degrees above the horizontal. Was that the angle? Yeah, 35 degrees. 35 degrees. I should say theta equals 35 degrees. And the distance moved is 65.3 meters. Like that. They also gave you the mass of the sled. Guys, does the mass of the sled have anything to do with how much work was done moving it? No. If they had a follow-up question like how fast is it moving, then the mass would matter. But right now, with the question they asked, the mass is a complete red herring number. You don't need it at all. So let's do work equals F dot D, which is that's the same thing as magnitude of force times magnitude distance times cosine of the angle between the two, right? Or how I might prefer to think of it is I'm going to slide that cosine over and attach it to the F and say the forward component is F cosine theta. And that moves forward distance D like that. So got 225 newtons. Cosine of 35 degrees. And that moves in that same direction forward 65.3 meters. Boom, boom, boom. Right, true. All right, so 225 cosine 35, 65.3. Right. All right. That makes sense, right? You do that. Right. So while you guys are catching up to that, I'm not going to use the full force because not all the force moves the sled forward. Only the forward component does. That's why I did F cosine theta. Came up with this right here. Now that since that's the forward component and the direction of motion is also forward, at that point I'm allowed to straight up multiply by the distance, right? If you like more definition types, you can actually multiply the cosine in any order you want. Now, importantly, it is the angle between the two vectors, the force vector and the displacement vector, right? So that's why I'm allowed to do cosine. the next example, we might have to be really careful about what angle we were talking about, but for now, we'll put it together. Chris, what are you guys getting for how much energy? You guys got a number?
35.4.
Ah, all right. I'm getting the same thing. All right, all right. 12,000 and something joules. There you go. Hey, that looks like about the same amount of energy as it took to lift the fridge on the last question, isn't it? About 12,000 joules. Look at that. Uh, actually, that's probably all I could really reasonably know is about 12 kilojoules. Right? Do I really know it's 0.35 exactly? Probably not. All right, guys, ready for next one? Number 67, escalator. Sao Lan has mass 52 kilograms. She rides up an escalator at Ocean Park in Hong Kong. This is the world's longest escalator with length 227 meters, an average inclination of 31 degrees. Now, guys, when they say inclination of 31 degrees, is that from the vertical or from the horizontal? From the horizontal, right? Up 31 degrees that way. Right? Now, careful about that. How much work did the escalator do lifting her up? So I get a picture going for 67. Okay. Let's have escalator. Let's call this angle theta to be 31 degrees. Let's call this distance is 227 meters. Let's get Sao Lan on here. Give her a mass of 52 kilograms. She's going all the way up. Draw her at the top too. So, right. So there's like a height change here. Call us H. Right. Which they did not give us that number, but we can calculate it. Right? And that might be helpful. Right. Hey guys, do you think that the work done lifting her up that escalator is equal to the potential energy she ends up with at the end? Kind of like the fridge, right? Which should be something like mgh, right? So work. Now, if I start from the definition of work, I could say, oh, that's F dot D, force dot distance. Let's do something like that, right? And I bet the force could be like her weight. You could think of it that way. I have to lift her weight up some height, right? Let's start throwing that in. Right, so in place of F, maybe I'll do mg. So that could be, guys, how many newtons does she weigh? Mg could be 520 newtons about. I'm going to round that to 520 newtons. Okay. And distance. Oh. Now, something to do with 227 meters, right? Except she wasn't lifted straight up 227 meters. So I still need one more factor here. Okay. Guys, what do I put in these blank parentheses right here? Okay, here's where you want to be kind of careful. Okay. So I'll show you guys the poster version of this. Okay. So back to this poster. Let's ignore the shopping cart or the sled. Let's look at these stairs over here. Hey, the stairs, that could be more like an escalator, couldn't it be? Right? Now, the guiding formula is still F dot D, force distance cosine theta. Right. But guys, if you take something upstairs, is there any work done in carrying it horizontally across the room? No. Right? Is all the work done in lifting it up the stairs? Yeah. So it really has to do with this vertical change. Right? And the angle between the force and the distance moved. Right. So I'm really only lifting with a vertical type force just to hold up against its weight. Right. I'm carrying it some distance that's diagonal, like a diagonal displacement. Right. Do you guys see the angle between those is from the vertical? Do you guys see that? Right. So I'm allowed to do ft cosine theta and play off that angle theta from the vertical. But let's go back to Sao Lan here. Guys, that angle is from the what again? Horizontal. So can I say cosine of 31 degrees? No, because that would be the wrong angle. That's like if I gave you the angle down here. Which if I did, guys, if I gave you this angle, this would no longer be cosine theta. It would now be what? Sine theta. That's what I need right here. I need a sine of 31 degrees, right? Because like here's your force, mg. Well, here I should split this way. Right, here's your height. So here's mg, and here's h. Okay. Alternatively, you could put in cosine of guys, if you really, really wanted to use cosine, if you're really stickler about that, you would not use 31 degrees. You would use how many degrees? Guys, what is this angle right here? 59 degrees. It is 59 degrees. Guys, cosine of 59 degrees. Is that the same thing as sine of 31 degrees? Yep. So now you got an option. You can either, you have to be really careful about what angle are you talking about. Okay. If you keep the angle they gave you, you actually have to switch from cosine to sine. If you want to stick with cosine, you have to find the complementary angle, which is 59 degrees. Okay. They both give you the same thing. Okay. So there's our weight, there's the distance moved. Whoops. Okay. But have to take the component. Whoops. 31 degrees. Okay. I'm getting this many joules of energy there. Right? Now, if this escalator is like hooked up to the power grid, I bet it is, and that power grid is probably hooked up to some power plants, right? Maybe there's some coal plants and some whatever they're using in Hong Kong to get power. Right? That's like that could represent sort of like how much coal had to be burned so that you could run the escalator and get her to the top of the hill. Right? Right. Let me try it with the cosine 59 degrees. That should also work. Do cosine 59 degrees. Yeah, I got exactly the same answer. Same thing. All right, you guys good with escalator? It's good? Oh, working. All right. Number 78. Oh, it's a graph. Guys, look at this graph. Force versus displacement. Force versus displacement graph. Is whenever in physics you see a force versus displacement graph, there's a really good chance you're going to be asked how much energy was transferred, how much work was done. And the answer is always just the area under the curve. Okay, that's all. Okay. Now, my poster version is very simply a constant force. Therefore, the area is a rectangle. Right? Your textbook question, well, it's not a constant force. It's always changing. But force versus distance, the work done is still the area under the curve. Okay. Now, what's the questions here? Calculate, calculate the work done to pull the object 7 meters. Now, guys, careful. Your graph actually goes up to 8 meters, but they said to stop at 7. Okay. So area under the curve. Can I split it up into all these shapes and say this triangle plus this rectangle plus this triangle plus this rectangle? Can you do that? That's exactly what we're going to do. So this is question A. The work done is equal to, right. Because what's the area of a triangle that's 2 meters wide and 20 newtons tall? What's that area? 1/2 base height, right? What's 1/2 times 2? Times 20? That'd be 20 joules right there. 20 joules. Right. So it's 20 joules moving at the first 2 meters. Right. Now that's an increasing force. Then the next meter. Ooh. Well, it's split up into a rectangle topped by a skinny triangle. So let's do this rectangle. What's 1 meter wide times 20 newtons tall? That's another 20 joules. On top of that's a triangle, 1 meter wide and 30 newtons tall. How big is that triangle? Guess what's 1 times 30? Divided by 2. 15 joules. Okay. And last part, it looks like most of the work was done actually just in this last part here. So there was a constant 50 Newton force that acted for 1, 2, 3, 4 meters to bring you up to the 7 meters. Okay. Guys, what's 50 times 4? 200. And then newtons times meters gets you to joules. Right? I think that should be the answer right there. All I have to do is add those bits together. 200, 20, 40, 50, 255 joules. I think that's it. 255 joules. Okay. Okay. So if somebody's pulling that with their muscles, that's how much energy came out of their muscles. If they ate breakfast that day, if it's hooked up to a battery, that's how much energy was pulled out of the battery. The energy came from somewhere. Okay. Question B. Calculate the power. Ooh, power. Let me find my power poster. Ah, here it is. But before I show you guys, power is equal to, it's a fraction. Guys, it's what divided by what? Let's remember this right here. Okay, work per time. All right. It's a rate of energy transfer. Energy transfer, that's work. And if I ever say like the rate that something's happening, well, that's divided by time. Like how fast does that happen? So work over time. Okay. And here they just said, okay, so 255 joules was the answer to part A. That's how much work was done. They just said it all happened in 2 seconds. Right? 255 joules of work. This all happens in 2 seconds. So the number on my screen is this. Guys, that number has units. Guys, what is joule per second? What is that? How do you measure power?
Watts.
Watts. Yeah, watts. Capital W could be watts as a unit. Let's say P power equals 127 watts. Right? Hey, could there be a light bulb that's maybe 127 watts? Would you want to look straight at it? Oh, it'll be super bright. Number 81. Ooh, a pulley system. Lifts 1345 Newton weight, a distance of 0.975 meters, so maybe almost 1 meter, but a couple centimeters short. Paul pulls the rope, a distance of 3.9 meters, exerting a force of 375 newtons. So we got 2 forces and 2 distances. Hey, I think they're setting up what I was talking about earlier with mechanical advantage. You guys remember this right here, right? I think this is about to be a really helpful poster. Here's the thing. See, question A, what's the ideal mechanical advantage? Question B, what is the, let's call it actual mechanical advantage? And question C, what's the efficiency? So one thing at a time. Number 81. Okay. So ideal mechanical advantage. Okay. Now, if we're talking about ideal mechanical advantage, that's what distance did I pull? So I'll call it distance in compared to the distance the weight moved. I'll call it distance out. Ratio of the distances moved. Because it's just based on geometry, right? If you just look at the geometry or whatever you're working with, then you can know what is the ideal mechanical advantage. Okay. So, okay. There's that other one. Just ready to go to. So what are those distances? So he had to pull a long distance, right? Yeah, 3.9 meters. He pulled 3.9 meters of rope. And the weight only moved 0.975 meters. Right. Guys, just at a glance, does that look like about a 4-to-1 ratio? Just think 4-to-1. Right? And usually with ideal mechanical advantage, you end up getting integer values. Maybe there's a way for that not to happen, but you usually get that, especially with pulley systems. I wonder if this is going to be a 4-to-1 system. It is 4-to-1. Right? So that means if he wants to move this thing up 1 meter, he has to pull 4 meters of rope, which he's almost done. He's almost there. He's almost got it 1 meter tall. He has to pull 4 meters of rope. If that's true, do you guys see that this right here could possibly be his system? Right, see 1, 2, 3, 4-to-1, 4-to-1. Right? Maybe rig this up. Maybe these 2 pulleys are actually one single double pulley. It's the 2 independent wheels side by side. Maybe. Right? They could be different ways. Actual mechanical advantage. Now, the actual mechanical advantage is the ratio of the forces. I'm going to do force out over force in. Okay. Notice I've changed 2 things. I changed distance to force, but I also swapped what's in and what's out, or what's on top and what's on bottom. You see in over out versus now I just did out divided by in. The reason being I want this to show up something like 4-to-1, but maybe it's going to be a little bit short of that. Do you guys think the actual mechanical advantage in terms of forces is going to be almost 4-to-1, but maybe a little bit less? Maybe like 3.9-to-1, maybe, possibly. Okay. Let's see what the actual numbers are. 1345 Newton weight, 1345 newtons is being lifted. That's like the output force. But Paul only has to pull with 375 newtons of force. Just like tomorrow, you guys will do the same thing. Like, wow, I got super strong from this mechanical advantage pulley system. 1345 compared to 375. That is, oh, look at there's 3.59. I'll round it to 1, maybe something like that. Yeah, guys, look at that. That's almost a 4-to-1 ratio. Just a little bit less. Okay? Because yeah, maybe there's some frictional losses, maybe those ropes aren't exactly vertical. Those are two main reasons why you might not get the full mechanical advantage out of that. Right? That's good. All right, one more question about Paul here. How efficient is the system? Okay. So this is going to be Greek letter eta. Okay, so it looks like an N with an elongated tail. That's eta. And we're going to use that for efficiency. Okay. Now there's different ways we could get this. You could do work out compared to work in, which is F out, distance out over F in, distance in. Okay. If you ran the numbers that way, that would give you efficiency. Okay. Or since we got the mechanical advantages, here's a fast way to get it too. Actual mechanical advantage compared to the ideal mechanical advantage. It's going to be the same ratio. If I just do it that way, 3.59 compared to 4. Right? See, what is that mechanical advantage? 0. I'm going to round this a little bit. 0.90. Guys, as a percentage, what is that as a percentage? 90%. So this machine is 90% efficient. That means if Paul does 100 joules of work, say from his muscles lifting 100 joules, only 90 of those joules actually transfer to lifting the weight. And the other 10 joules maybe go to like frictional losses, maybe it heats up a little bit, things like that. All right. You guys think you're ready for the lab tomorrow? All right. How about chapter 11? You guys ready for chapter 11? All right, here we go. Ooh, it sounds like I'm going bankrupt, but that's okay. We all good. We're in physics. Number 57. Tony has a mass of 45 kilograms and is moving with a speed of 10 meters per second. Okay. Let's read the questions first. What is this kinetic energy? And question B, we're going to slow him down to half of his original speed. Now what's his kinetic energy? And question C says, what's the ratio of his kinetic energies in parts A and B? Okay. So, all right, got mass equals, let's see, 45 kilograms. And his initial speed is 10 meters per second. And then later on, here, I'll go ahead and do this too. Later on, he's going to go 5 meters per second. Okay, so those are all given values. Given. Right, all good. Right. Before I go plugging and chugging on this, which we're about to do, I want to see if you guys can get the answer ahead of time, so you guys can see the big picture. But what's the formula for kinetic energy? 1/2 mv squared, right? Like energy of motion. Guys, energy of motion has something to do with motion, speed. That's the V. Mass also, right? So something like that, right? Okay. So think ahead a little bit. Guys, if he's eventually going to have half of his original speed, you guys ready for this? Here's a proportion question. He's going to have half of his original speed, 10 down to 5. What proportion of his kinetic energy is it going to have by the end of this process? Huh? It's like factor of 4, right? Yeah. So it'd be 1/4. Because if you throw a factor of 1/2 on this V, don't forget that 1/2 also gets squared. 1/2 times 1/2 is 1/4. Isn't that right? Okay. That's going to eventually be the answer to question C. I want you guys to see that before we go plugging and chugging. But let's do that. Let's throw all the numbers in. And then you'll see from the numbers that's also true. Tony's original kinetic energy. So 1/2 mass initial velocity squared. See, how many joules of kinetic energy is that? 1/2 mv squared. That's like this many joules. All right, there's the answer to A. It's not too bad, right? 1/2 mv squared. Question B. Now he slows down to this half as fast speed. What's his new kinetic energy? Well, K final. Still 1/2 mv squared. 1/2 m. But now the speed is half the speed. And square that. In my calculator, I can just scroll up, scroll over where the 10 was. I can just put a 5. Gives me that many joules right there. All good. And then question C is, what's the ratio? I guess there's two ways to go about this. You could do K final over K initial, or you could go K initial over K final. However you think of it. So 562.5 on 2250 or 2250 compared to 562.5 joules, 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 joules. What is 2250 compared to 562.5? Okay. Now, if you've been following, you guys know when I hit enter, there better be one number that pops up on my screen. What's that ratio? Yeah, it's a 4-to-1 ratio. That's right here. It's 4-to-1, or if you did it the other way, you get 1-to-4. However you did it. All right, so that could do it right there. So the takeaway from this one is this is a proportional question. Whenever you double your speed, you're going to have 4 times the kinetic energy. But you guys have seen a lot of those proportional type questions throughout this class. You guys see that? All right. So like here, if you're in your car and you drive up some speed, take some gasoline to get there. If you drive up to double the speed, it takes 4 times the amount of gasoline. Ooh. Number 60. Oh, speaking of cars, here's a car braking to a stop. A 14,000 Newton car is traveling at 25 meters per second. The brakes are suddenly applied. The car slides to a stop. You guys have seen braking cars. I have a poster for this one. It showed up in your energy table. We saw this as an open system. We solved this one. Do you guys remember that day we took to solve a car brakes to a stop? I solved it 2 different ways. I've solved it in terms of dynamics, kinematics, and I solved it in terms of this energy. And we got the same braking distance. That's in your notes from a few days back. Tell that. So this one should look really familiar. The average braking force, back to here, says is 7,100 newtons. How far will the car slide? There's the classic question right there. How far is the car slide? All right, number 60. Okay. So I'm going to throw some numbers on here. They said the weight of the car was 14,700 newtons. I'm going to throw a little insert here. Guys, the mass of the car is approximately how many kilograms? 1,470. All right. I'm going to call G, Earth gravity, 10 meters per second squared. I normally do. What else they got? We've got initial velocity was 25 meters per second. I think that's over 50 miles an hour. So think like highway speed. And they did tell you the friction force, which is kind of interesting too. Later on, here guys, after we solve this, I'll ask you guys, what do you think was the coefficient of friction? So hold on to that, a little bonus question. But here's the full force, is 7,100 newtons. Okay. So what's the braking distance? We may consider all these to be givens, although we kind of derived one of those, whatever. Okay. All right, so here, get a little picture going. Little turtle car, mass, initial velocity, and final velocity is 0 after some braking distance. All right, there it is, set. I did make that messed up line with a ruler somehow. Okay. So do you guys remember we solved this with an open system? An open system meaning you can do work on the system and maybe the energy change. It looks like this. Sum of energy initial plus or minus the work done. I'll say minus work done by friction. Gives you sum of energy final. Right? So you can think of it that way. Right? You guys seen this a few times, right? Good review here, right? Okay. Guys, what kind of energy did the car start out with? Kinetic. What's the formula for kinetic? 1/2 mv squared. Oh yeah. Okay. Oh, minus work done by friction. Ooh, guys, what's the formula for work? Force times distance. In this case, it would be the braking force, the friction force, times the stopping distance, because it acts over the full distance. Okay. And how much energy? What kind of energy at the very end? 0 joules. Okay. The car is not in motion. It stopped, so it doesn't have any kinetic. It did not roll up any hills, which could have helped it slow down, but that didn't happen, so there's no potential. Just 0 joules. Okay. It looks like all the energy went into Probably thermal, like heating up the road and heating up the tires. I think that's where it went. Okay. Let's get some numbers in here. 1/2 mass is 1470. That's kilograms. The initial speed, should throw initial right there, was 25 meters per second. That's being squared. The friction force they told you was 7,100 newtons. The braking distance we're solving for goes to 0. All right. All right. There's a couple of algebra steps, but I think I got enough paper for one more line. So can I do this? Can I just get a hard number here? Let me do that. Let's 1/2 times 1470 times 25 squared. Okay. So guys, this comes out to 459,000 some joules. Some crazy number of joules. Okay. Can I add 7,100 D over to the other side and then divide both sides by 7,100 newtons? Can I do it? Okay. So this divided by 7,100 newtons, you guys seen that algebra step a bunch of times in here. Okay. Skip a little bit. Braking distance is, do you guys get the answer? 64.7 meters. Oh yeah, 64.7 meters right there. Okay. I just took, guys, all I did is took 459,000 joules. Then, okay, add this over, divide by 7,100 newtons. That's what I did. You get 64.7 meters. Okay. All right, guys, good there? All right, so let's go back, let's circle back to a question of what approximately would be the coefficient of friction between the tires and the road, allowing this car to come to a stop. Because they could have given that to you and had you solve for the friction force. So a little free-body diagram right here. Here's the car, weight, mg, upward force, normal force. And if it's moving to the right, I bet the friction force, FFR, is acting to the left. That could be the free-body diagram, right? Right there. Okay. Who could tell me? Guys, what is the coefficient of friction? Who knows? Isn't coefficient of friction like the ratio, the friction force compared to the normal force? You guys remember that? Okay. And the friction force is 7,100 newtons. And the normal force, hey, what would the normal force be? 14,700 newtons? Wouldn't it just have to balance out the weight? So I'm going to divide by that. We get 0.48. So approximately 0.5, right? 0.48, 0.5, somewhere there. Okay. I think the coefficient of friction is almost 0.5. Okay. What does that mean if you're on the road? I think that means that it probably just rained earlier today and the road's all wet. And this guy's going highway speed. Guys, this guy's on US 1, zooming on a wet road. He slams the brakes. And how much distance to come to a stop? About 2/3 of a football field. Does that sound about right? I think it does. I think it does. Yeah. All right. You guys good on car braking? All right. Next one. 15 kilogram cart is moving at velocity 7.5 meters per second down a level hallway. Okay, level hallway meaning there's no height changes. So we can throw out all the MGH. That's not going to matter. A constant force of 10 newtons acts on the cart, and its velocity slows down to 3.2 meters per second. What was the change in kinetic energy of the cart? How much work was done on the cart? And how far did the cart move while the force was acting? Okay, guys, those first two questions, the change in kinetic energy and the work done on the cart, that's the same question. I'm going to get some numbers down here. Mass is 15 kilograms. Initial velocity, 7.5 meters per second. Final velocity, 3.2 meters per second. And, well, I'll just say F for force is 10 newtons, but I'm going to throw in a negative sign because it is slowing it down. So maybe the negative can help. I'll consider those given values. Okay. And like I just said, those first two questions, A and B, are really the same question. And that's because of something called work energy theorem. Work energy theorem says if you do some work on some object and it's not changing height, so no potential energy, it's not going to springs, there's no friction loss, that all that work is going to go into a change in kinetic energy, which is exactly what we have here. We have a level surface. So A and B is the same thing. So I can say change in kinetic energy, which is the work, is 1/2 mv final squared minus 1/2 mv initial squared, right? Just the change in kinetic energy, right? That's all. Right? So let's get some numbers. Got 1/2, 15 kg. It ended up at 3.2 meters per second. Square that. Minus 1/2 mass. It started at faster. Then square that. If I take that difference, that's the change in kinetic energy. Furthermore, I know that that's the work that was done slowing it down. So same thing. 1/2 mass. You guys getting that too? Like negative 300 something joules. As the change in kinetic energy. Oh, well, that must have been the work that the force did, slowing it down. Right. Now, question C says, what distance? Right. Oh, well, work is force times distance, isn't it? And since we know the work and we know the force, I could solve for that distance right there. You guys can do that too? Set up that expression. That's going to be negative 345 joules is negative 10 Newton force acting for some distance. Down here, I'll say distance equals, and we'll get the answer. Oh, actually, you know, I don't even need a calculator for that. Okay, guys, what's the answer going to be? What's that distance equal to? 34.5 meters. Oh yeah, there's the answer. Let's do that. That makes sense, right? You do some work on something that changes the amount of energy in the system. And if it's all kinetic, then you set up the equation that way. All good. Okay. All right, now guys, these last two questions, we only got two more to go, 81 and 84. Since we're getting close to the end of class, I will show you guys how to set these up and solve these, but I'm going to leave these to you guys. Okay. So these last two questions, I want to get my posters ready because I can solve them both with, here we go, these posters. Right. So number 81, Hakeem throws a 10-gram ball straight down from a height of 2 meters. The ball strikes the floor at a speed of 7.5 meters per second. What was the initial speed of the ball? Right. Now that's not exactly the same as this poster, but it's really similar because there are two different ways you could solve Hakeem throwing the ball. Actually, here, I'll set this up with you guys. What number is this again? 81? I think I got enough time. I can kind of set this up. Okay. So we got a 2 meter height change. H equals 2 meters. Hakeem throws the ball down at some speed. I'll call it V naught. And the ball, when it's about to crash into the ground, is moving at a faster speed. Call it V final. Okay. Two ways to solve this. Do you think you could use this third kinematic equation right here? You could have solved this like 2 months ago. Say, look, I'm solving first throwing speed. I know the crash speed. I know the acceleration is the gravity field. And this displacement is the height change. It's all there. It's all there. You can solve for how fast did he throw the ball. You see that? Right. Now that's the old way of doing it. The new way is with conservation of energy. And there's what kind of energy at the top? mgh plus 1/2 mv naught squared. What kind of energy at the bottom? Is there any mgh? No. It's all 1/2 mv squared, but it's mv final squared. 1/2 mv final squared. Okay. Right. Now is this sum of energy equal to this sum of energy? Is that equal to that? Yeah. Even though they gave you the mass of the ball, could you, if you want to, cancel off the mass of the ball? They could have given you the mass of any ball. And if the speeds were the same, then the answer would still be the same. Okay. So solve for, yeah. You know, gravity field, bing. You know, the height, 2 meters, bing. You know, the crash speed, bing. And for that matter, they did give you the mass, bing, bing, bing. Could you plug all that in and solve for the throw speed? You do that, right? Okay. So there you go. There's two different ways to solve that. The old kinematic way and the new conservation of energy approach, but they give you the same answer. And last one, number 84. Suppose a chimpanzee swings through the jungle on vines. If it swinging on a vine, is that like the last lab that you guys did? Swinging on a vine? Oh yeah, I think you guys were swinging on vines in here. Health inspector. It won't tell OSHA. If it swings from a tree 13-meter long vine that starts at 45 degrees from the vertical, what is the chimp's velocity when it reaches the ground? I think the answer is exactly right here. Guess they told you the length. They told you the angle is 45 degrees. You could solve this with conservation of energy. You do have to do some geometry to figure out this height change. Although it's kind of soft here anyway, right? Now, you do also need to know the gravity field. Can you guys pick your favorite gravity field? Plug that in. Right? I mean, the answer is right there, isn't it? Right. All right. So I'll leave you guys with those last two. Oh yeah, we have a minute left in class, so we're doing pretty good. All right. Guys, puzzles are due on Friday. And that's a wrap on today.